In a yard in Nebraska, a 130-ton freight car with no crew, no engine, and no brakes rolls down a hill by itself and slams into a standing train. Nobody stops it. This is not an accident. It happens roughly every 25 seconds, all night, on purpose. This is a hump yard. The call is roll it free, uncouple the car, and let gravity do the sorting. It works because a freight train is not what you think it is. It's not one vehicle heading to one place. It's a temporary bundle of unrelated shipments that must be torn apart and rebuilt again and again as they cross the continent. And this system, strange, violent, precisely controlled, is how freight really moves. The scale of this operation is defined by physical space. A railroad classification yard operates as an active sorting machine rather than a simple storage lot for idle trains. In the railroad industry, this process of using gravity to assemble trains is called humping, and the facilities designed for it are hump yards. Across North America, these yards serve as the primary processing centers of the rail network. When a mixed freight train arrives from hundreds of miles away, its cars are rarely bound for the same destination. One might carry timber to a paper mill in Maine, while the next holds chemicals for a plant in Texas. A single yard must systematically untangle these massive mixed commodity shipments and organize them by where they need to go next. This is where the hump itself comes in. By pushing cars over an artificial hill and letting them roll freely into a series of classification tracks, railroads bypass the slow, fuel-intensive process of using locomotives to push and pull every individual car. Instead, they let gravity do the heavy lifting. The term hump yard turns what looks like a series of runaway railcar collisions into a standardized, highly engineered routine. It is a system that transforms a continental network of disconnected tracks into a singular, flowing pipeline, processing thousands of cars every day through a sequence of calculated, gravity-powered impacts. At major hubs, this method is deployed on a massive scale, coordinating the flow of thousands of railcars daily across hundreds of miles of internal track. This terminology matters because it reframes what appears to be a violent accident into a standard, highly precise operating procedure. To understand why railroads build trains by sliding multi-ton steel boxes down artificial hills, it helps to dismantle a common misconception. Most people view a freight train the same way they view a passenger train or a cargo ship, as a single cohesive vessel traveling from one origin to a final destination. In reality, a freight train is a temporary marriage of convenience. Every train rolling across the continent is a fleeting collection of unrelated shipments. One car might hold timber from Oregon, another chemical tanks from Houston, and a third auto parts destined for Detroit. Each of these individual cars has its own specific path, its own customer, and its own schedule. This means a single car will change partners, routes, and trains multiple times during a single cross-country journey. It might start on a short-line railroad in rural Georgia, transfer to a major carrier in Atlanta, and end up on a local delivery track in Chicago. Because of this constant shuffling, industry data indicates that a typical freight car spends the vast majority of its life stationary, sitting in yards, waiting to be sorted, or idling in transit. The train itself is assembled, run for a few hundred miles, and then completely torn apart. The hump yard is the specialized machine built to handle this endless cycle of assembly and disassembly. It is the logistical filter that constantly reorganizes thousands of rolling components into a coordinated, nationwide pipeline. To transport freight across North America, railroads must solve a persistent mathematical problem. The geometry of the continent does not match the layout of the tracks. A single shipper in Oregon might need to send 3 carloads of timber to Miami, 2 to Chicago, and 5 to Dallas. But there is no single direct track connecting that origin to all of those destinations, and running a dedicated locomotive for just a few cars across thousands of miles is an economic impossibility. Instead, railroads rely on consolidation. They bundle those timber cars with hundreds of other shipments destined for the east, creating a massive mixed commodity train that stretches over a mile long. But this train cannot stay together for the entire trip. As it travels across the network, it must constantly be broken down, sorted, and rebuilt. This necessity exposes a surprising reality of freight logistics. A typical freight car does not spend its life rolling across the countryside. According to data from the Association of American Railroads, a single freight car spends roughly 70% of its life completely stationary, sitting in yards, waiting on sidings, or idling in transit. The actual trip consists of brief, high-speed sprints interrupted by long stretches of waiting. The classification yard is where this waiting turns into active reorganization. It is the physical place where routing complexity is forced to deal with physical reality. Here, the abstract lines on a shipping manifest become heavy steel realities. When a mixed train arrives, its cars are sorted strictly by their next destination, regardless of what they are carrying. A car carrying fresh produce might be coupled next to one filled with scrap metal, simply because both share the same immediate destination 300 miles away. This constant, repetitive sorting is the primary engine of the entire network. To make this massive sorting machine work, railroads do not build towering peaks. They build a subtle, engineered hill. At Union Pacific's Bailey Yard in Nebraska, this artificial rise consists of an eastbound hump standing 34 feet high and a westbound hump of just 20 feet. This modest height is intentional. A higher hill would generate too much speed, turning a controlled roll into a destructive runaway. The sorting process begins not with a dramatic plunge, but with an agonizingly slow, deliberate crawl. A heavy switch locomotive couples to the rear of a long string of cars, often called a cut, and begins to shove them up the gentle incline. The locomotive moves at a steady pace of just a few miles per hour. This slow approach is critical. It establishes a predictable, rhythmic spacing between each car. As the cars creep upward in a single, unbroken line, they remain fully coupled, their heavy steel knuckles locked together. But as each car nears the absolute peak of the hill, the locomotive's active roll comes to an abrupt end. At the crest, a worker walking alongside the slow-moving train pulls a mechanical lever, releasing the coupler pin. At this exact moment, the physics of the yard shift completely. The uncoupled car, pushed just over the apex, is no longer connected to the locomotive's braking system or its mechanical power. It is suddenly on its own. This is the precise handoff point. Up until the crest, every inch of movement is dictated by the active burning fuel of the locomotive and the direct control of the train crew. Once the car crosses that invisible line at the top of the rise, human power steps aside. The locomotive stops shaping the car's path, and pure geometry takes over. What began as a tightly controlled mechanical push becomes an independent, gravity-powered descent into the vast maze of tracks below. The steel knuckle of the coupler slides open. In a fraction of a second, the mechanical bond connecting a 130-ton loaded rail car to the locomotive's braking system is severed. The car is now completely disconnected. There is no safety tether, no physical cable, and no crew member on board to apply manual brakes. As the car clears the apex of the hill, gravity takes complete control of the descent. It is suddenly a runaway object, driven solely by the physical grade of the artificial rise. Yet this is not an aimless, chaotic slide. The car is entering a highly coordinated steering network. As the car gathers speed down the incline, the switches ahead dictate its direction. The locomotive that pushed it to the crest remains behind, already preparing the next car in the queue. The rolling freight car must travel its path alone, guided only by the steel rails and the automated turnouts shifting beneath its heavy steel wheels. The separation creates an immediate physical problem. A 130-ton steel mass accelerating down a steep grade will quickly reach speeds capable of destroying anything in its path. If left unchecked, the kinetic energy of the descent will result in a violent, destructive collision at the bottom of the hill. To prevent disaster, the yard's control systems must now solve a complex physical equation in real time. Every foot of the descent requires absolute predictability, precise timing, and a calculated method of braking before the car reaches the stationary trains waiting on the track below. To the untrained eye, letting a 130-ton steel box roll freely down a hill to smash into a stationary train looks like a recipe for total destruction. Inside these cars are paper rolls, automotive parts, fresh produce, and fragile consumer goods. A single violent impact should, by all laws of common sense, reduce the cargo to scrap. Yet the cargo survives because the entire yard is engineered around a single governing metric: 4 miles per hour. This is the standard coupling impact limit established by the Association of American Railroads. At 4 miles per hour, about the pace of a brisk walk, the kinetic energy of a rolling car is just enough to trigger the automatic knuckle coupler to lock. At this speed, the car's heavy, shock-absorbing draft gear can safely dissipate the force of the collision before it ever reaches the freight inside. The engineering objective here is to make the impact completely predictable. If a car rolls too slowly, it will stop short of its target, blocking the track and stalling the entire yard's operation. If it rolls too fast, it violates the 4 miles per hour limit, risking severe damage to both the vehicle and its contents. Every piece of technology in the classification bowl, from the track scales that weigh the cars to the automated retarders that grip the wheels, exists solely to enforce this precise, unyielding limit. The math must be exact, protecting both the cargo and the flow of the network. To understand why railroads chose controlled collision as their primary assembly method, one must look at the physical connection holding these trains together. For decades, coupling was the most dangerous job in North America. During the 19th century, railroads relied on the link and pin system. To connect two cars, a worker had to stand directly between the moving vehicles as they came together. At the exact moment of impact, the worker manually guided a heavy iron link into a pocket on the opposite car and dropped a steel pin to lock it in place. A mistake of inches meant crushed fingers, lost limbs, or death. In 1873, a dry goods clerk named Eli Janney patented a solution that changed the industry. Janney's automatic knuckle coupler took inspiration from human hands. He designed two interlocking steel knuckles that clasped together and locked automatically upon impact. When two cars collided, the force of the contact pushed the swinging knuckles closed, sliding a heavy internal pin down to secure the connection. This mechanical shift converted a lethal hazard into an automated routine. The impact itself became the trigger for safety. The transition was not immediate. Railroads resisted the expense of retrofitting thousands of cars with Janney's design, prompting federal intervention. In 1893, Congress passed the Railroad Safety Appliance Act, making automatic couplers and continuous air brakes mandatory for all interstate trains. After a grace period to allow for compliance, the law became fully effective in 1900. The results were immediate. Coupling casualties among rail workers plummeted. The act of crashing cars together was no longer a threat to survival. It was the mechanism of a safer, more efficient network. By standardizing Janney's knuckle design, the industry transformed the dangerous point of contact into a reliable, self-locking connection. Today, when a 130-ton rail car rolls down the hump and strikes a stationary train, that same mechanical design ensures the connection locks instantly, converting raw physical momentum into a secure, unified train. If every railroad car were identical, building a train with gravity would be simple. But a hump yard processes an unpredictable mix of rolling physics. A fully loaded tanker weighing 130 tons behaves completely differently than an empty flat car. Send them down the same incline under the same conditions, and one might glide smoothly for half a mile while the other stalls before even reaching its destination track. The railroad industry calls this physical variance rollability. Predicting how any given car will behave is the core engineering challenge hidden within gravity sorting. The moment a car is released at the crest, it becomes a rolling physics experiment. To ensure it hits the standing train at exactly 4 miles per hour, the yard's control systems must calculate its unique rolling resistance in real time. This calculation is a moving target. The base friction of a steel wheel on a steel rail is incredibly low, but a dozen external variables constantly warp the equation. Loading weight, bearing age, and wheel wear all change the baseline. Cold winter air thickens axle grease, increasing resistance, while high summer temperatures soften the steel wheel rims, changing the coefficient of friction. Track geometry adds another layer of drag. Every curve and turnout a car negotiates on its way to the classification tracks adds friction, scrubbing away valuable momentum. Then there is the wind, which can act as a sail or a brake depending on wind speed and direction. Before the car even reaches the first break, sensors along the track must measure these forces. They weigh the car in motion, gauge its speed using radar, and assess current weather conditions. The task is no longer just letting a car roll. It is predicting exactly where and when that specific car will stop, turning an apparent runaway into a mathematically controlled descent. To translate calculations into physical force, the track itself must become a brake. This is the job of the retarder, a heavy assembly of hydraulic and pneumatic machinery built directly into the rails. As a 130-ton car descends, it passes through these devices, which act as a physical editor for the vehicle's speed. Rather than applying brakes from inside the car, heavy steel brake shoes rise up to flank the rails, squeezing the inner and outer sides of the spinning wheel flanges. The machine applies a massive clamping force, ranging from 30 to 120 kilonewtons of braking pressure per wheel. Controlled by proportional valves, hydraulic systems can alter this pressure in less than a quarter of a second, while pneumatic hydrodynamic configurations settle in under 0.4 seconds. This rapid response allows the system to continuously adjust its grip as the car rolls through, shaving off exactly enough kinetic energy to match the target speed. This physical wrestling match produces the hump yard's most famous and unsettling signature, a piercing, metallic shriek. This ear-splitting scream is often mistaken for the sound of a system under destructive strain, or perhaps just a noisy byproduct of heavy industry. In reality, the noise is the sound of active, real-time control. It is the physical manifestation of kinetic energy being converted into heat and sound as the steel shoes bite into the wheel flanges. Each screech is a moment of mechanical judgment. The system is measuring the car's momentum and deciding exactly how much speed to bleed off. By the time the wheels emerge from the far end of the retarder, the car has been slowed to its precise target velocity. The runaway has been tamed, ready to coast quietly toward its final connection at a safe 4 miles per hour. Behind the physical screech of the brakes lies a live, high-speed computing environment. The hump is not merely a hill with mechanical brakes. It is an active, real-time physics engine operating continuously. As each car begins its descent, track-mounted sensors immediately start collecting telemetry, turning raw kinetic motion into digital data. An in-motion scale built directly into the track structure measures the exact weight of the rolling car, categorizing it instantly as light, medium, or heavy. Overhead and trackside radar units track its instantaneous velocity, calculating how fast it accelerates down the initial steep grade. But weight and speed are only part of the equation. To determine how much brake pressure to apply, the yard's automatic speed control system must know where the car is going and what stands in its path. This is where track occupancy counting becomes essential. The target track in the classification bowl is not a blank slate. It is a constantly shifting queue of heavy steel. If a track can hold 50 cars and 45 are already parked there, The newly released car only needs to roll a short distance. If the track is empty, it must roll nearly half a mile. The computer constantly registers the exact location of the last stationary car on every single track, recalculating the remaining distance to the target in real time. Every single car presents a distinct, multivariable physics problem that must be solved in milliseconds. The system takes the weight, the real-time radar speed, the distance to the target, and current atmospheric conditions, including wind speed and ambient temperature, and runs them through a predictive rollability algorithm. At modernized facilities, machine learning-enhanced prediction models like Pilot calculate the exact pressure profile required for the retarders. It determines whether to apply 30 kilonewtons of force or 120, commanding the hydraulic valves to adjust the steel-on-steel grip in less than a quarter of a second. On average, this calculation occurs every 25 seconds, 24 hours a day, processing roughly 3,000 cars daily. During peak operations, the system can accelerate this cadence to handle a car every 15 seconds. There is no room for manual estimation or human guesswork on this hill. Every impact at the bottom of the slope is the direct result of a digital calculation, translating raw data into physical deceleration to ensure the car lands at exactly 4 miles per hour. For all its complex computing and precision braking, the hump yard has a hard physical limit. Walk through any classification bowl and you will eventually spot a bold, stenciled warning on the side of certain freight cars: "Do not hump." This simple stencil acts as a warning label for the entire yard. It marks the boundary where the gravity sorting machine must stop. Certain cargo simply cannot survive the routine physical impact of a 4-mile-per-hour coupling. These exclusions typically include pressurized tank cars carrying highly hazardous chemicals, flat cars loaded with sensitive military hardware, or specialized loads carrying delicate industrial machinery. For these cars, even the most carefully calculated descent is too high a risk. When a car marked "Do Not Hump" arrives at the receiving yard, the automated system must halt its progress. The car cannot be pushed over the crest and allowed to roll free. Instead, it must be isolated. A switch engine and crew must manually couple to the car, pull it out of the queue, and guide it through the yard to its target track. This manual bypass is slow, labor-intensive, and highly disruptive to the yard's continuous rhythm. It takes extra locomotives, additional crew hours, and precious track space to do by hand what gravity usually does for free. But this operational friction serves a larger purpose. By highlighting what must be handled with extreme care, the stencil reveals just how routine, reliable, and deeply standardized the world of gravity sorting has actually become for everything else. In 1975, North America operated 152 active hump yards. By 2026, only 36 remained. This dramatic reduction was driven by precision-scheduled railroading, a business strategy that swept the industry in the late 2010s to prioritize point-to-point service and cut fixed overhead. Under this model, the massive centralized hump yard was no longer viewed as an essential logistics engine, but as an expensive, maintenance-heavy bottleneck. Railroads argued that they could simplify their networks by eliminating the middleman. Instead of sending every car to a massive central facility like Bailey Yard, they could sort them into blocks at their point of origin. By running longer, unified trains directly to their destinations, carriers could bypass the hump entirely, allowing them to retire costly retarder systems, automated switches, and control towers. But this operational streamlining created immediate friction. For many shippers, closing these gravity machines did not speed up deliveries. It shifted the sorting burden to smaller, flat-switching yards that had to shuffle cars back and forth on level ground using manual locomotive power. In 2018, shippers filed a wave of complaints with federal regulators, reporting severe gridlock and missed connections. That same year, Class 1 railroads faced $1.2 billion in service-level fines from the Department of Transportation. Surface Transportation Board metrics later revealed that average transit times for grain shipments rose 10 to 15% following the closures, while railroads saved an estimated $1.5 billion annually on yard operating expenses. Shippers faced rising demurrage fees and longer transit delays. The rapid dismantling of the hump network exposed a fundamental tension within modern railroading: the pursuit of a streamlined, low-cost balance sheet versus the physical reality of a resilient, high-capacity shipping network. The debate hinges on a simple operational truth: gravity is free, but locomotives are not. Pushing a 130-ton car over an artificial hill requires only a momentary mechanical shove. Shuffling that same car back and forth across a flat yard requires constant fuel, active crews, and continuous engine maintenance. By dismantling the hump, railroads traded long-term network efficiency for immediate operational savings. But this optimization on paper has real-world consequences. The loss of centralized gravity sorting has reorganized the movement of everyday goods, forcing shipments of grain, timber, and manufacturing parts to linger at regional choke points. This shift defines what kind of rail network the continent wants: a streamlined pipeline running fixed, point-to-point trains, or a flexible, high-capacity system designed to gather and sort diverse cargo. As Class 1 carriers continue to balance operating ratios against transit times, the silent, gravity-powered hills that remain stand as a reminder that the most efficient way to build a train might still be the simplest: letting physics do the work. Today, as modern railroading favors speed over sorting, these massive gravity machines are slowly grinding to a halt. Yet, the paradox remains: in a world obsessed with precision, letting a 130-ton steel giant roll free was the ultimate act of efficiency. Because while logistics will always evolve, one law of physics remains undefeated: gravity is free, but locomotives are not. What do you think of this industrial marvel? Let us know in the comments.